In this video, we're going to start our last unit. This last unit is going to be on square roots. So we're going to take a look at what a square root is. We're going to define it. We're going to practice finding square roots and take a look at some properties of square roots. So in this video, we're going to find the square roots or focus on finding square roots of numbers that have rational square roots. So their square roots can be a rational number or the ratio of two integers. Okay, so let's consider the following. So we have operations that, for lack of a better way of saying it at this point, undo each other in our number system. So for example, let's say I take the number 5 and I add 10 to that. So I take 5 and I add 10 to that. I don't need the 10 to be so thin, do I? I'm going to add 10. So that works out to be 15. So I can take the number 5 and I can perform the operation of addition. I can add 10 to that and get 15. But we have an operation that will undo that. We have subtraction. So I could take that 15 that I got. So I've got this 15 and I then could subtract 10. And what that would do for us is it would get us back to the 5 that we started with. Now you're going to take a look at this idea in a lot more depth in later courses, but for now, let's just think about the fact that I can add 10 to a number. In this case, I get 15. But what if I don't want that 15? What if I have this 15 and I'm like, oh man, I would much rather have what I started with. I wish I could just hit the reset button and go back to that 5 that I had to begin with. So I could take that 15, I could subtract 10, and it would return me back to the 5 that I started with. So this idea of addition and subtraction, they can undo each other. So addition and subtraction can undo each other. And we have other examples. Let's say I start with the number 6. Let's say I start with the number 6 and I multiply that by 4. So I do multiplication. Well, 6 times 4 gives us 24. But again, what if you have the 24 and you're like, oh man, I really didn't want to do that. I want to go back to that 6 that I had. I really want to go back to that 6. Well, then I could just divide by 4 and that'll take me back to the 6 that I started with. So multiplication by 4 and division by 4, turns out they can undo each other. So once again, we see two things, two operations. So multiplication and division can undo each other. And again, you're going to take a lot closer look at this idea in later courses. But for now, let's just think about the fact that you can add and subtract, and they can undo each other. Multiplication and division can undo each other. Well, one of the things we've discussed recently is um, exponents and what an exponent means and how to work with exponents. So the question we want to ask ourselves is, what would undo an exponent? What would undo an exponent? So what if you say squared something and you squared it, got a number and thought, oh, I don't want that number. I want to go back to what I started with. Okay, so what if you had the number 10 and you squared it and you get 100 and you're thinking, wait a minute, I don't want the 100. I want to go back to the 10 that I started with. I want the 10 that I started with. What would undo that exponent? Well, it turns out, as you're going to see, um, square roots will do that. So we could find the principal square root of 100, and the principal square root of 100 is 10. So it turns out square roots can undo an exponent of 2, and that's going to be our focus in this video. Okay, so finding a number's square root can undo an exponent of 2. So I did one example up there, but let's do another one real quick. So for example, let's say you've got 3 and you square it. Well, we know that 3 squared is 9. Again, what if you have the 9, you've got this 9, you're like, oh, darn it, I don't want the 9, I want to go back to that 3 that I had. Well, you can find the square root, the positive square root of 9, which is 3, and get back to the 3 that you started with. Now, you may remember from earlier that when you square an integer, what you get is called a perfect square. So this is, handwriting's not very good there. 9 is an example of what we call a perfect square, because you take the integer 3, square it to get 9. So since you square an integer to get 9, we call 9 a perfect square. And then 3, this is a square root of 9. So we're just introducing you to some vocab we're going to use again here. So with this idea in mind, let's go ahead and let's define what a square root actually is. So mathematics is built upon definitions. So we need a formal definition that we can follow, so we know exactly how to find a number's, turns out, both square roots of a positive number. So our definition so if you have a number a and you square it and you get a number b, then the number a is a square root of that number b. So it's a fairly short definition. So if you take a number and square it, whatever the answer is, whatever you squared is the square root of the output. So a squared is b, so a, without the exponent, a is a square root of whatever the output was, the answer, the result, b. And then note, if that number a is an integer, B, oops, B is called a perfect square. So you can see using the example we have right above us, we have 3 squared. We have 3 squared is 9. So 3 is the A, 9 is the B. And sure enough, over here, the square root of 9 is 3. So 3 is a square root of 9. So 3 squared is 9. Then 3 is a square root of 9. So 3 squared is 9. So 3 is a square root of 9. So we can see that in the example just above. So occasionally we'll grab a calculator to help with really complicated ones. But for the most part, we can do a lot of square roots without the help of a calculator or technology. And we can do that because we actually know you guys have been using a lot of perfect squares in your math career. Um, so why don't we go ahead and make a list of some useful perfect squares. In other words, ones we're going to use a lot. So this is going to be a list of perfect squares that we use quite a bit. So for example, 0 squared is 0. So 0 is a perfect square. 1 squared is 1. 1 is a perfect square. 2 squared is 4. So 4 is a perfect square. So this column here, these are the perfect squares, what you get after squaring the integer. So 3 squared, 9. 9's a perfect square. Then 4 squared. So again, the perfect squares are these, the ones that are highlighted. So these are perfect squares that we're going to use a lot. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. But there's more than that. We're actually going to use some more than that. So 11 squared is 121. 12 squared. 13 squared. 14 squared. So here's some more perfect squares that we're going to see fairly often. The bigger ones we won't see as often, but you'd be surprised how often those will show up. And then from here, we're not really going to make a list, just keep in mind that we can extend this idea. So for example, um, we know that 3 squared is 9. So if I do 30 squared, it's 900. Or 4 squared is 16. So if I do 40 squared, that'd be 1600. So there are some other perfect squares that we should recognize really quickly, but we're not really going to make a list. They're just basically extensions of these earlier ones that we already know. So if you see, for example, if you see 4900, hopefully you recognize that as a perfect square because that'd be 70 squared because 7 squared is 49 and then 70 squared would be 4900. So there are some bigger ones that are basically just extensions of these earlier ones. So the highlighted, what's highlighted, those are the perfect squares. Okay, so the highlighted numbers are the perfect squares. So those are a list of some useful ones that we're going to see quite often. All right, moving on from that, the next important thing for us to play around with and understand is every positive real number has two square roots. More specifically, let's actually name it. Every positive real number a has two square roots, and those are positive square root of a and negative square root of a. So every positive real number a has two square roots. So this symbol, get a little bit more specific here. This symbol here represents the positive, or the word you're going to hear me say more often, principal square root. So right here, this is the positive or principal square root of a. Then over here, this is the opposite of that. Opposite just meaning negative. Since this denotes the positive one, then you throw a negative out front, you're just basically saying, okay, take that positive one and find its opposite, or negative principal square root of a. So now why is this true? Why does every positive real number a have two square roots? Well, I'm not going to provide a proof, but let me try to convince you. So for example, if I take positive 4 and I square it, I get 16. So this shows us that, so this means 4 is a square root of 16. But we know from middle school that if I take negative 4 and I square it, that would also give me 16, because a negative times a negative is a positive. So this means negative 4, or the opposite of 4, is a square root of 16. So the 16 has two square roots. So the number 16 has two square roots. So the square root, my color is wrong here, 4 and negative 4. It has two square roots, 4 and negative 4. So every positive number, positive real number, such as 16 was the example I did, has two square roots, a positive square root and a negative square root. But the positive square root is called the principal square root, and we have a symbol for that. So if you want the positive square root, you use that symbol. All right. Next up, the number 0 only has one square root, and that is 0. So 0 is not a positive number nor a negative number. Remember, 0 on the number line separates the positives from the negatives. So 0 doesn't have a positive or negative version of itself. So if you're supposed to find the square root of 0, well, there is only one number that's squared that gives you 0, and that's 0. So um, 0, I won't use any color for this one. 0 squared is 0, but there is no such thing as negative 0. Um, negative 0 is not really a thing. 0 is not positive or negative. It separates the positives and negatives on the number line. So 0 only has one square root, where um, all the positive numbers have two square roots. And then one other thing, the square root of a negative number is not a number. Well, we'll just be specific here. So the square root of a negative number is not a real number. So if you're asked to find, say, the square root of negative 25, what would that be? Well, it turns out it wouldn't be any number we've ever heard of. Um, there is no number that when you square it comes out to be negative 25. When you square any number that we know of, it never gives you a negative answer. If you don't believe me, get out your calculator and try it. Every single number you can think of, when you square it, it comes back as either a positive number or 0. We never, ever, ever have had a number that we've studied so far that when you square it gives you a negative answer. So basically what this means is if you come across the square root of a negative number, for now, we don't know what that is. So we would just say that it's undefined. It turns out later in math, you'll see we do have a definition that can work with these. But for now, they're just not a real number. So a better answer would be to say it's not a real number. If you put undefined, that would be okay too, because at this point it is undefined. We don't know, we don't have a definition for that. Okay, next up, we got two properties that we're going to practice with. I'm going to offer these without proof at this point. So if A and B are positive, so if you have the principal square root of A times B, one of our properties is you can go ahead and split that up and do it this way. So if you have the principal square root of A times B, you can write it as the principal square root of A times the principal square root of B. You can separate it into two principal square roots. And it turns out you can do the same thing if you have a fraction to begin with. Now, for the one that has a fraction, it turns out a could be 0 here. It wouldn't hurt anything if a was 0, just not very useful, because 0 divided by anything is 0. You just get 0 for the answer. But technically, a could be 0 for that bottom one. A could be 0 for the top one too. Again, just doesn't provide us with anything useful. Square root of 0 is just 0. So your homework, you're just going to practice finding square roots and using these properties. Now, you won't need to use these properties all the time, but they do prove helpful from time to time. So all we're going to have you practice at first is just trying to come up with, on your own, using the calculator as little as possible. Basically, can you find square roots of positive numbers? Okay, so let's go ahead and practice a few. So let's find the indicated square root. We might ask you to find more than one, so I'll put an S there. All right, so for example, let's say you're asked to find the principal square root of 81. Principal square root of 81. So since you're asked to find the square root of 81, you're basically trying to find what number, when squared, is 81. Well, 81 is one of our perfect squares. So let's go back up here. 81 is one of our perfect squares. We're supposed to recognize that as 9 squared. So we want to get to the point where we see 81 and realize, oh wait, that's 9 squared. So if I want the principal square root of 81, I just have to realize, oh wait, that's 9 squared. So the principal square root of 81 is just simply 9. So whatever number's in here, right, when you've got it's being squared, whatever number is being squared, that would be our principal square root. Let's say you're asked to find the opposite of the principal square root of 16. Well, let's just first figure out what the principal square root of 16 is. So let's not worry about the fact that it's the opposite. But 16 is a perfect square. We're supposed to recognize that. We're supposed to recognize that 16 is just simply 4 squared. So that 4 is what's being squared. So that's the square root. Now what about the opposite? Well, the principal square root of 16 is 4, and we just want the opposite of that. So we want negative 4, or the opposite of 4. So there's my 4, and then that negative, or we just remember the whole time we just wanted the opposite of whatever the principal square root of 16 is. Well, the principal square root of 16 is 4, so I just want the opposite of 4, negative 4. So when you step back and look at it, really the negative out front didn't do anything. We didn't really need to do anything with it. It was just saying that our final answer is going to be the negative square root for 16, which is negative 4. Sometimes you might be asked for both of them, so they'll put a little plus minus. So in this case, they're asking you what are both square roots of 144? What are both of them? Now, as you know by now, I'm not a big fan of the plus minus symbol. So when I would do, if I see this, I'd say, okay, they're just asking me for both square roots. So I would just do this as two separate problems. I'd say, okay, what's the principal square root of 144? Well, 144 is one of our perfect squares that we're supposed to recognize. 144 is 12 squared. 12 squared. So I'd say, okay, look, this is just 12 squared. So the principal square root of 144 is 12. But they did ask me for the opposite, the negative square root also. So the work wouldn't be any different. They also want me to give the negative square root. So 12 and negative 12 both. In other words, that's the symbolic way of saying, hey, what are both square roots of 144? Well, what if we have a fraction? What if I'm asked to find the principal square root of 169/16? Well, that seems pretty complicated, except for we had a property that said you could split that up into two square roots. So I could write this as the principal square root of 169 and the principal square root of 16. Well, 169 is one of our perfect squares that we're supposed to recognize. So there's 169, and that's 13 squared. So I'd say, okay, principal square root of 169, that's just 13 squared. 16, that's 4 squared. So I would get 13 fourths. So 13, that's the principal square root of 169. And then 4, that's the principal square root of 16. So I get 13 fourths. So it looked like it'd be a complicated square root because of the fraction, but really you just split them up and do the principal square root of the numerator divided by the principal square root of the denominator. Well, what if they give you a really large number, like 5,184? So if you have a really large number, it's possible that that large number um, is just comprised of smaller perfect squares. So 5,184, you can get 5,184 by taking 64 times 81. So 64 times 81 is 5,184. Well, one of our properties was that if you have a square root, you can split it up into the product of two square roots, two principal square roots. So I have the principal square root of 64 times 81. So I can write that as the principal square root of 64 times the principal square root of 81. So I can split it up into two square roots. So 64 is just 8 squared, and 81 is 9 squared. So this is really just 8 times 9, which is 72. Now you might be thinking, well, wait a minute. How am I supposed to know 5,184 breaks up into 64 times 81? Well, um, from time to time, we will use a calculator to help us with the larger arithmetic. Um, but sometimes you're going to recognize, depending on the number, you're going to recognize that, hey, I know that breaks up into a few other numbers. You might recognize it on your own. Otherwise, um, if you need to grab a calculator to help you with your arithmetic, you can. Um, but what this work is showing us, what this little bit of work here is showing us, is that 5,184 is actually a perfect square. If you take 72 times 72, you get 5,184. But that's not one of the perfect squares that you're expected to recognize. So remember, we had a list earlier of perfect squares that you're supposed to recognize, and 5,184 wasn't one of the perfect squares I expect anyone to recognize. It is a perfect square, but not one that I'm expecting you to recognize. All right. Now, don't make sure you're paying attention to what you're being asked to do. Don't get in a hurry and just assume an answer without thinking about it. So, for example, what if we were asked to find the principal square root of 121 squared? So make sure you stop and think about what you're being asked to do. So when you square something, you're taking it times itself. So that's the principal square root of 121 times the principal square root of 121. Well, using our property, two square roots times each other, you can write as one square root. So I have the principal square root of 121 times the principal square root of 121. So I could write that is like that. And 121 times 121 is 121 squared. Oh, It turns out that if I just square a square root, all I get for my answer is the number that was under that square root sign. So it's with that in mind, if I had the square root, if I had the principal square root of 17 and I squared it, that should just be 17. So when you square a square root, it just gives you back the number under the square root sign. So while we're on the topic of not being in a hurry, let's look at this one. So the square root sign is a grouping symbol. This is a grouping symbol. So this thing right here, this is a grouping symbol. And that means we have to do everything under the grouping symbol first for the order of operations. So under the grouping symbol, I've got 13 squared minus 5 squared. So I have to do the exponents first. Then I have to do the subtraction. And then I can do the square root. So be careful. You have to follow the order of operations. Do not assume you know what the answer is going to be. All right, let's do one more, and then we'll call it. Let's say you had a fraction with big numbers in it. Well, earlier we saw that you could split it up and do the square roots separately, so that'll make things a little easier. 100 is a perfect square. That's 10 squared. And 2304 is a perfect square, but it's not one that I would expect you to recognize. So since it's not one you would recognize, if you need to, you can use a calculator. Otherwise, notice that it ends in 4. It's even, so it's possible that some of the even perfect squares, like 4 or 64 or 36, it's possible that some of the even perfect squares would go into that without a remainder. So it turns out that if you divide 2304 by 4, it's 4 times 576. Well, 576 is not one of the perfect squares you're supposed to recognize, which is okay. That's okay. 576, let's keep going. So the top is 10. 576, since that's not one of the perfect squares that we recognize, we could maybe divide it by some of those other perfect squares. And it turns out if you divide it by 9, you get 64. You get 64. So the top is 10, the bottom is principal square root of 4, principal square root of 9, principal square root of 64. So we get 10, and then we know what all of those are. Those are all common perfect squares. So this is 2 times 3 times 8. And then we can simplify here. So that 10 and that 2, that's 5. So we get 5 over 24. Get 5 over 24.